Welcome, everyone. Um, Announcements. Your Next Achieve is available due Monday morning. And that's about it. I will have a different office hour tomorrow. I'll post an announcement. I think it's going to be in the morning because I have afternoon meetings that were scheduled. But I will post that announcement today to let you all know. And then there are a couple events coming up at the university that I just wanted to share with you. So the first one is Connection. So you may have seen that poster in this building or in other buildings. So this is a science-inspired art expo. So students and faculty and staff have created different types of art inspired by science, and that will just be on display. So that's all next week, Monday to Thursday. Starts at 3 p.m. and goes till 8 p.m. every day. I don't remember where it is, but if you find the poster, I'm sure that will say where you can go to see it. And that event is free, so you're welcome to just like walk through, see what some of your classmates or faculty have created, just to kind of see. Another one is the Detroit Mercy Theater Company is putting on a play called Photograph 51. This is all about Rosalind Franklin, so you may have learned about her in the past in your biology course. But she contributed to the development of identifying the structure of DNA, but her work was not properly acknowledged in the past, so the play is all about that kind of portion of history. So that starts next weekend and is the weekend after as well. And then the third event will be February 15th. I will give you more information about this once we have the flyer put together. But Chem Club is hosting a Women in Science event. So this has historically been pretty well attended and attendees have enjoyed their time there. So we have 6 panelists that are coming. They are women that work in the science field. At the event, you'll sit at a table with other students and one of the panelists, and you'll be able to just kind of have a conversation with them. I'm sure they'll share about their career. And then at a certain time, the panelists will get up and move to a new table, and so you'll be able to talk to someone else. So we have some lawyers with a science background. We have doctors. I don't remember the whole list, but there's a lot of different careers represented by the panelists that are coming. So I will remind you of that as we get closer, but that's in the evening on February 15th. So lots of cool events coming up just to keep in mind. On Monday, we ended the class talking about solutions. So we're now talking about mixtures of substances. We define these 3 terms, what a solution is. The solvent is what determines the state of the solution, and it's usually what is in highest concentration. And then the solute is a component that's not the solvent, so usually lower concentration. And solutions can be gaseous, liquid, or solid. And then I had you all complete this learning check, which we'll go through here. So first we have a solid solution, a metal alloy. Metal alloy is a mixture of different metals. It looks like one metal though. You can't identify different metal atoms present. But for a certain metal alloy that's made of 85% copper, 4% lead, 6% tin, 5% zinc by mass, question is, what is the solvent? Well, in this case, we label the solvent as the metal that's in highest concentration. So for the alloy, that is copper. Its highest concentration, so we label that as a solvent. Everything else that's mixed in with copper are solutes. We have an example with coffee. Americano coffee is made with water and espresso, and the question here is, what is the solute? Well, if you're drinking coffee, that's mostly water, and in the water, the espresso bean is dissolved. So the espresso is the caffeine, different flavors. And so the solute, remember that's what's dissolved in the solvent. So in this case, that is espresso is the solute, and water is the solvent. Then our last one was a question about the atmosphere. So this is a gaseous solution. Our atmosphere is 78% nitrogen, 21% oxygen, 0.04% carbon dioxide, 0.96% other gases. So then the question here is, what is the solvent? Again, like the metal alloy, this is the component in highest concentration, so nitrogen. And then every other gas would be considered a solute as part of that solution. Questions on any of these iClickers? Okay, so we'll talk about what makes something likely to form a solution, and then properties of these different types of solutions. So the ability of substances to form solutions depends on, these should be like indented, it depends on these two factors: the substance's natural tendency towards mixing and intermolecular forces. So we'll talk about both of these. Something that is a liquid is a little bit easier to mix together than if you have two solids and you're trying to mix those solids together. That would be difficult. And then intermolecular forces helps us understand how different molecules or different substances will interact with each other at a molecular level. Okay, so we'll focus on liquid, then gas, then solid. So liquid solvents can dissolve other gases. Liquid solvents can dissolve other liquids, and liquid solvents can dissolve solids. So in water, in liquid water, that is the solvent in pop, soda, but the fizziness from soda is carbon dioxide gas that's dissolved in that liquid. So carbonated beverages are prepared by dissolving gaseous carbon dioxide in water, and then flavors and sugar and whatnot is added to the soda as well. So that's a liquid dissolving a gas. An alcoholic beverage like vodka is prepared by dissolving liquid ethanol, so that's the alcohol part of alcoholic beverages, with water. So that's a mixture of a liquid and a liquid. That's a liquid solution. The water dissolves the ethanol. Salt water, like an electrolyte solution, is prepared by dissolving solid salt in liquid water. So now we have liquid dissolving a solid. So if we have a liquid solvent, it can dissolve gases, it can dissolve liquids, it can dissolve solids. Not all gases or all liquids or all solids, but it can dissolve certain ones of all three. And if we think a little bit more about this salt solution, if we're adding an ionic solid into water, here's what's happening. We've got the ionic lattice. So this is a lattice image like we've seen when we were talking about solids. When you add an ionic lattice to water, it remains a solid until the water starts interacting with the ions in the ionic solid. So remember that water is polar. It's kind of shown right here, but I'll draw a Lewis structure as well. So that the oxygen to hydrogen bond is polar in the direction of oxygen. So the hydrogens have a partial positive charge and the oxygen has a partial negative charge. So we have partial charges on water and we have formal charges in the ionic lattice, the positive and negative charges. So as you add the ionic solid to the solution, the cations, which are positively charged, are attracted to the oxygen in the water, which has a partial negative charge. So you can see the oxygen attracted to the positive cation, then the water molecules will surround the cation, and then this gets dissolved in water. We've got water surrounding that cation. For the anion, the negatively charged ion, the partial positive hydrogens on water are attracted to that negative anion. So it surrounds the anion, and then we have that ion dissolved in solution. So this takes time for that to occur. When you first pour a solid, an ionic solid like salt, into water, mix it around, it will still look like a solid. You can see the solid particles. And then as water starts surrounding and breaking apart that ionic compound, it dissolves into the solution. Okay, so solutions so far with liquid as the solvent. Next, we've got solutions with gases. So gaseous solutions or gaseous solvents can dissolve gases, or they can dissolve other gases that are normally liquids or solids. So we'll do some examples of that at the end. When we have a gaseous solution, we say that each component behaves independently of the others. This was one of our assumptions when we were talking about the ideal gas law, that gases in a mixture behave independently of one another. So we can calculate the partial pressure of one and partial pressure of the other, and it doesn't depend on what else is present. So that's what we're saying there. Okay, so if we think about air, air is a gaseous solution with molecular nitrogen as the solvent, and then oxygen is in second highest concentration, so that's the primary solute. This is a gaseous solution dissolving another gas. Humid air, so when we have a really humid day, the air, so mostly nitrogen, has dissolved water vapor. So that is now a gas, but it is typically a liquid. Water is typically a liquid at room temperature. So this is a gas solvent dissolving what was a liquid, the water vapor. And then our last example here, if y'all have smelled mothballs before, they certainly have an odor. And this odor originates from a solid molecule, naphthalene, that sublimes in air and becomes a gas and is then dissolved in the atmosphere and air. All right. So there we have gaseous solutions. Now let's talk about solid solutions. Solid solutions generally are difficult to prepare because mixing of atoms or molecules is difficult because metallic atoms or molecules do not move freely. So if you take a sample of silver, a sample of gold, and try to mix them together, they're not mixing, right? They stay as their own components. To mix those metals, you have to melt them and then mix those together. An example of that is a metallic alloy that we kind of talked about in that learning check, where this is multiple different metal elements mixed together to form that alloy. Our coins, like pennies, dimes, nickels, those are all alloys. They're multiple metals. A penny is not just copper. Compounds, plastics to adjust strength. So these are other solids that have different compounds added to adjust their strength. Just like how a plastic bag, that is plastic, but that's not as strong as a plastic container, like, I don't know, or a plastic like the back of this, right? Like that's a stronger plastic, has different solids in that plastic. Steel is not an element, it is a metal, but steel is made of iron and carbon. So carbon atoms are added to an iron sample, and then that makes steel. So all these are different solid solutions. All right, so we can understand or predict if two substances will make a solution based on their intermolecular forces, and we can describe, we have two types of substances, miscible, which refers to substances that form solutions in all proportions. So two substances that are completely miscible will always mix together. They'll always form a solution. So an example of this is water and acetone. These are two liquids at room temperature. It doesn't matter which is in higher concentration, so which is the solvent or which is the solute. Any ratio of water and acetone will always mix together and form a even and evenly distributed mixture of the two. The opposite side of that are insoluble substances. So this describes a solute that cannot dissolve well in a solvent. An example of this is sodium chloride, so an ionic compound, NaCl. In gasoline, gasoline is mostly octane. Octane is a CH3 group, that's 6 CH2s, and then a CH3. So all nonpolar bonds, a completely nonpolar molecule, that will not interact with an ionic compound that has a positive charge and a negative charge, cation and anion. These two do not interact with each other. So if you add salt to gasoline, it's going to remain a solid. It will not dissolve in the octane. That's a result of different intermolecular forces between these two compounds. So we can use this rule, like dissolves like, meaning that substances with similar intermolecular forces will dissolve and create a solution. So substances that dissolve in each other usually have similar types of intermolecular forces. So an example is water and methanol. We know water, H2O, can hydrogen bond. And then methanol also has an OH group that can hydrogen bond as well. Both molecules are polar. Both molecules exhibit hydrogen bonding interactions. So water and ethanol can hydrogen bond with each other. They can mix together and form a solution. They are miscible. Octane, which we just talked about, completely nonpolar molecule, only carbon to carbon and carbon to hydrogen bonds. And cyclohexane, which is another nonpolar molecule with only carbon to carbon and carbon to hydrogen bonds. They are both nonpolar. They both only have dispersion forces, so they are miscible with each other. Similar intermolecular forces. But if we take one from our first example, one from our second example, they're not miscible. So octane, nonpolar, carbon to carbon, carbon to hydrogen bonds. And water, completely polar, oxygen to hydrogen bonds only, they do not interact with each other. They will not form a solution. Octane and water, if you add them together, they'll form two layers, where you have one layer of water, one layer of octane. For something to mix with water, it has to disrupt the hydrogen bonding interactions between water molecules. Remember, water molecules are held together through hydrogen bonding interactions. Well, something that's nonpolar is not going to disrupt those hydrogen bonding interactions. It's not going to mix together. So these two liquids are immiscible. They do not mix together to form a solution because of the different intermolecular forces, dispersion in nonpolar molecule versus polar molecule that can hydrogen bond. A good example of this, like you may have seen in your own life, is salad dressing. So salad dressing usually has water or vinegar. Both water and vinegar can hydrogen bond. So that would form a mixture or a solution together. And then there's usually an oil, like olive oil or some other type of oil, that's present in salad dressing as well. Oils are mostly nonpolar molecules. Water and vinegar are polar. So when you look at like Italian dressing that has a clear vinegar layer and a clear oil layer, if you let that settle, you'll see two different layers. One is vinegar and water, one is oil. If you shake it, mix it together, then you can mix it, you can force the mixing, but then if you let it sit again, it'll separate into two different layers. And again, that's because oils are nonpolar, they have dispersion forces. Vinegar or water is polar and has hydrogen bonding interactions. So we've got a picture of this on the next slide. This is a picture of a beaker with water and octane. Water is on the bottom because it's more dense. Less dense will be on the top. But the key here is that water is these are all hydrogen bonding interactions between water molecules stay together. These are dispersion forces between octane molecules, those stay together. They do not interact with one another. They form two separate layers. If you have this and add methanol to this beaker, The methanol, remember, can hydrogen bond and interact with water. So methanol will mix in that bottom layer. If you add cyclohexane, which is nonpolar, dispersion forces, cyclohexane will mix with the top layer. So molecules that have similar polarities and as a result intermolecular forces will mix together. If that's not the case, then we have two separate layers. And that's what we mean by like dissolves like intermolecular forces will dissolve. But there are some substances that are soluble, or some molecules that are soluble in many substances. Acetone is a good example. So acetone, this is the structure, the Lewis structure. Acetone has a lot of different uses. Two uses that come to mind relevant to my life, you might have different uses. But one is that this is a common solvent in organic chemistry, and it's commonly used to clean glassware. It's also the main component in nail polish remover. So acetone dissolves a lot of other substances. That's why it's used as a glass cleaner in chemistry labs, because if you have a water solution in your beaker or an oil solution in your beaker, something in between, you can use acetone to clean it out. It'll dissolve what's in there and then you can pour it into the liquid waste bin. That's because there are different parts of this acetone molecule that can interact with different, or can exhibit different types of intermolecular forces. So down here where we have CH3, carbon CH3, these areas are nonpolar areas where dispersion forces can exist. Nonpolar, nonpolar. So the molecule can interact with molecules that have dispersion forces. There's also a polar bond. The carbon to oxygen bond is polar, and that can interact with other molecules that have dipoles. So it can interact with nonpolar molecules and molecules with dipoles, polar molecules. And we have an oxygen with non-bonding electrons that can hydrogen bond, for example, with water, can accept a hydrogen bonding interaction from water. So this molecule has polar, nonpolar, and hydrogen bonding capabilities. Generally, the part of the molecule that's nonpolar is similar size to the polar part of the molecule, but one can outweigh the other depending on the size of the molecule. So let's look at this next page here. We have four substances, propanol, butanol, four substances, propanol, butanol, pentanol, and hexanol. You don't really need to worry about the names. Look at the formula. Each of these have an OH group, so they're all alcohols, but they have a different length carbon chain. Propanol is completely miscible with water. Butanol is miscible, but only up to a concentration of 1.1 molar. If you have a 1.1 molar solution of butanol in water, and then add more butanol, it won't dissolve. It won't be miscible with the water. And then we decrease even more for pentanol and hexanol. So with the people around you, try to give a molecular or chemical explanation for this trend. Why does the solubility decrease as we go down the table for those substances? All right, what are some of your ideas? What is it about the molecule that changes its solubility? Yes, what?
We keep adding more carbon, probably like add more forces.
Okay, so we add more carbons as you're going down the table, which adds more dispersion forces. So what does that mean about the solubility? Why does that decrease the solubility?
Because it's more groups the water can't interact with.
More groups that water can interact with. Yeah, that's a good way to put it. So if you're looking at each of these molecules, while they all have a polar end, that OH group, that OH group can interact with water. It can hydrogen bond. When we look at hexanol, we have this long 6-carbon chain that cannot interact with water. So all of this would not be soluble in water. Only the small part can interact. In propanol, that's a much smaller carbon chain, so that's a smaller part of the molecule with dispersion forces. Overall, propanol is more polar because the ratio of nonpolar to polar is smaller. Then hexanol, which is overall much more nonpolar. This whole section is nonpolar, and remember, like dissolves like. So with a much larger nonpolar area that's less soluble in water than propanol, which has a smaller nonpolar area. Something like soaps and detergents, they have a polar part of the molecule and a nonpolar part of the molecule. So if you're using soap to clean your dishes, you want the soap to wash away with water. So the soap particles need to interact with water. They need a hydrogen bond. But you also want soap to interact with oils and greases on your plates or whatever you're washing. So the nonpolar part of a soap molecule is miscible with oils and greases. The polar part is miscible with water, so you're able to wash it away. So if you Google structures of soaps or detergents, you'll see nonpolar and polar part of the molecule. Okay, so we can use intermolecular forces to understand or predict substances that will dissolve in other substances. Now, let's talk about solubility of different types of solids. Covalent network solids. This is like diamond. We talked about these at the end of chapter 12. Diamond, graphite, quartz. All of these are solids that are formed just as covalent bonds. So a diamond is a carbon covalently bonded to other carbons, which are covalently bonded to other carbons. They're not held together by intermolecular forces. These solids are insoluble in all substances. They may react with specific liquids or vapors, but this is a formal chemical reaction. This is not dissolving a substance. On the other hand, molecular solids, these are ibuprofen. Ice was another example. Remember, these solids are individual molecules, covalent molecules that are held together by intermolecular forces. So those intermolecular forces can be disrupted, and these solids can dissolve in certain solvents. But we use the same principles, like dissolves like. So molecules that have hydrogen bonding capabilities can dissolve in water and cannot dissolve in oils. Nonpolar solids can dissolve in nonpolar solids. So an example of another molecular solid is sugar or glucose. This image down here, if you see all these dashed bonds, these are hydrogen bonding interactions to water. Here's a hydrogen bond to water, hydrogen bond to water. Everything else that's not the water, that is a representation of glucose. So I'm going to circle glucose here. That's glucose in the center, and then in all these locations it's showing hydrogen bonding interactions. This is a molecular solid, and these hydrogen bonding interactions explain why glucose is highly soluble in water. Each OH group on glucose, there's 1, 2, 3, 4, 5. Each of those can hydrogen bond with a water molecule. So as you add glucose, if you're adding solid sugar to water, that sugar first will disrupt hydrogen bonding intermolecular forces between water molecules. The water molecules will disrupt hydrogen bonding forces between glucose, and then hydrogen bonding interactions between water and glucose will form and the glucose dissolves. Now, glucose dissolves in water because it has all those locations where it can hydrogen bond. We go to this next slide here, looking at a few different types of vitamins. Now, one thing I want to point out here is, let's look at the first vitamin. This is a shorthand representation of organic molecules where every single atom is not drawn out. But if we look at vitamin E, anytime a line ends, that represents a carbon, and any bend also represents a carbon. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. In this chain, there are 17 carbons. There's also carbons in the ring and branching off the ring. So line ends and bends represent where a carbon and hydrogens are. If there's any other atom, those are drawn out. So keep that in mind as we think about this question. So vitamins are required for proper function. They are not synthesized by the human body, but they are present in foods that we eat and supplements. So vitamins fall into two categories. They can be fat soluble or water soluble. Fat soluble dissolve in fatty hydrocarbon-like tissues in the human body. Water soluble vitamins, of course, dissolve in water. So a few vitamins are shown here: E, A, B5, B6, C, and D. Looking at these structures, categorize these into fat soluble and water soluble. Now remember, going back to that table, even though there's an OH here, there's more of a nonpolar part of the molecule, so this has stronger dispersion forces. Keep that in mind as you're looking at these structures. And I have a couple of these transformed into an iClicker. So as you work on this, try to answer those iClicker questions, identifying certain vitamins as fat soluble or water soluble. Remember to consider, of course, intermolecular forces and any large portion of nonpolar bonds will impact vitamin D. Is everyone into the question? Like you have access? All right. 30 more seconds if you're submitting. Try to get yours in. All right, I think everyone's in. Okay, so let's go through each one. I'm going to circle them in red for fat soluble, blue for water soluble. Looking at vitamin E, we have an OH group here. We have an oxygen here, but we also have like 30 carbons that have a nonpolar area in the molecule. So this nonpolar part of the molecule outweighs the one or two atoms that can hydrogen bond. So this is more likely to dissolve in fat than it is to dissolve in water. So this is a fat-soluble vitamin. If we look at vitamin A, this is similar. We have one area that can hydrogen bond, but a whole lot of carbons and hydrogens that are nonpolar. So dispersion forces outweigh that one location where hydrogen bonding can occur, and this is a fat-soluble vitamin. Next, we have vitamin B5. We have an OH group, oxygen, nitrogen, oxygen, oxygen, oxygen. All of those areas can hydrogen bond. And we don't have a long nonpolar chain here. So this is a vitamin that is water soluble. Similarly, vitamin B6. We've got two nitrogens that can hydrogen bond, two oxygens that can hydrogen bond, and again, no long non-polar chain. So this is another water-soluble vitamin. Vitamin C, 1, 2, 3, 4, 5, 6 locations where hydrogen bonding can occur, and no long non-polar chain is another water-soluble vitamin. Vitamin D, the last one, we have one OH group and the rest is all nonpolar. So this is a fat-soluble vitamin. So notice for D, vitamin D, E, and A, each of those do have a polar bond, but the nonpolar part of the molecule is much larger, contains more atoms. None of this would interact with water at all. All of this would interact with fat nonpolar molecules. So vitamin, yeah.
Can you specifically show where it's like
For vitamin D, yeah, it's just where an oxygen is. So this is polar right here.
non-polar?
Oh, all of this is nonpolar. These are all carbon and hydrogen bonds. So it's all, yeah, these are all nonpolar bonds. Other questions? All right, we'll talk about, so this portion, the last slide, was about solubility of molecular solids. So these solids that exist as molecules. Oh, by the way, I have a vitamin D supplement that is vitamin D dissolved in olive oil. And you just take a drop of that olive oil and that gives you your vitamin D. So it dissolves in olive oil. Olive oil is like a fat type of molecule, nonpolar, dissolves vitamin D in it. Okay, so those are molecular solids. We'll talk about solubility of metals, metallic solids. These don't dissolve in water generally. So these are silver, gold, metals like that. Remember, these contain delocalized bonding networks, what I termed as the electron sea, where you have a bunch of positive nuclei and then electrons surrounding them. Those electrons can float around like the sea. But these networks have to be disrupted for a metal to dissolve, so that does not really occur. Metals also don't dissolve in nonpolar liquid solvents. So metals don't really dissolve in water, they don't really dissolve in nonpolar solvents, but they can dissolve in each other. And this forms what we've described as an alloy. So an alloy is a mixture of substances with metallic properties. Can be homogeneous or heterogeneous. They can be substitutional or interstitial. So substitutional, this is like sterling silver. So sterling silver, we have silver that's represented as the gray circles. These are silver atoms. And then in places where there would typically be another silver atom, a copper atom has replaced or substituted that silver. So that's what substitutional means. We've substituted the main component for a different atom. Interstitial, we have carbon steel as an example of this. This is iron. So those are the larger atoms, iron. And then in spaces between iron atoms are copper atoms. So that increases the strength of iron because there's less space between those iron atoms. So those are two examples of alloys. Again, these are often formed by melting the solid metal and mixing them together and then letting them cool and they'll form the solid. If you've seen a knife get made, it's pretty cool to see the liquid metal. Or like a sword, how they did that back in the day. It's pretty sweet. It can also be carved out of solid. Okay, so another example is an amalgam. So this is specific to mercury. We've kind of talked about mercury. This is the only metal that's liquid at room temperature. So this can dissolve other metals at room temperature. So an amalgam is any solution of another metal dissolved in mercury. There are certain metals in the periodic table, silver, gold, zinc, tin. These are all close to where mercury is on the periodic table. And so they are particularly soluble in mercury. Any questions so far? Okay, well, we're going to end a few minutes early. We're already ahead of my 9 a.m. class, so we'll go to the next slide on Friday.